pretty extreme yesterday. All right, big idea. Our extreme values. There's going to be an absolute maximum value or an absolute minimum value on a closed domain. Yes? On a closed domain if the function is continuous. Awesome. The extreme value theorem, which you guys wrote down from the AP Daily video, right? Extreme value theorem? Yes?
Yeah.
Okay. This is just a visual of that. Where could the extreme values come from? They could both be interior. By interior, just non-endpoints. They could both be, this is not supposed to be open, that was just an example. If they're both closed endpoints, they could both be endpoints. Or you could have a combination. You could have a minimum at an endpoint. You could have a maximum at an interior point, or vice versa, minimum and maximum at an endpoint there. So if we, yesterday we kind of covered this. How are we going to classify these? If they're just a high point nearby, local max, local min. These would be what we're going to consider smooth critical points. All right, smooth critical points. They could come from where f prime doesn't exist or a sharp point, or they could come from endpoints. Local extreme values, you don't necessarily have to write this down. It's kind of stupid. Local max if, what's a local max? Well, it's higher than the other ones around it. It's greater than the other, or equal to, I guess, the other ones around it, local, all right? Local extreme values, well, we have to look for where f prime doesn't exist. Oh, wait, hold on. This is not what I was trying to say. I think critical points is coming up. If a function f has a local max or local min at a value at an interior point of its domain and f prime exists, then the slope is 0. We talked about that. We talked about smooth changes in direction. This is what I wanted to get at. We're going to call these critical points. Critical points or critical numbers. Critical numbers are the x values where the derivative is 0 or fails to exist. Okay? Sometimes they're called candidates. Does a candidate have to get elected in real life? No. But it's still a candidate. It could be to elected office. Could be voted into elected office, right? In a similar way, we call these candidates, these critical points are candidates because at this x value, the slope was horizontal. Does that mean it's an extreme value? No, it's a candidate. It has to be tested. It has to be tested. It might not pass the test. Some of you can relate. All right, boom rest. Just kidding, man. Oh, you guys are great students. Did it hit home? Get close. Sorry. I like your hoodie, by the way. Is that a hoodie or is that 2 layers?
2 layers.
2 layers?
Mm-hmm.
Because I've seen them where they're
I have
like
a Saints youth football hoodie under this.
still fits, huh?
Undefeated that year.
Nice. Gotta represent.
Yep.
I'm liking the 2-layered look this year, guys. Really pulling it together.
Like,
yeah.
Appreciate it.
Must have rubbed off on Mason yesterday. Yeah, he influenced
Inspired.
a little bit.
Yeah.
So I was like, I will be like working. Yeah.
Maybe I'll wear the 2 layers tomorrow. Who knows? Yeah. Try to be cool. Mason and Tyler are also wearing flannels today. 2 layers. Mason just has a sweatshirt underneath, crew neck. Tyler has a hoodie. Both looking sharp. All right, finding extreme values. Find all extrema on the graph. Find all extrema. And we're starting off with a baby, just a little baby problem. All right, easy. We know what 2x cubed minus 6x plus 1 looks like. We're not going to always have that benefit. We're not always going to know what the graph looks like. Do we all agree? A cubic with a positive leading coefficient could look like something like this, correct? How many extrema are we expecting it to have? At least 2. Why am I saying at least? Cool.
Because it could be 1.
Could be, well, could it be 1?
Oh, extrema, no.
Critical point, I agree. It could have 1 critical point that then failed the test. Do you agree? That critical point would fail the test of becoming a max or a min. Do you agree? Fails the test. These would both pass the test. So what's the test? Does the derivative, what's going to allow it to pass the test? Does the derivative change sign? Very good. And how? Does the derivative change sign and how? Ready? Over here. The derivative before c, say we plugged in a number like, I don't know, some number before. Let's call it a. What's the derivative going to be at a? Positive. What's the derivative going to be at b? Positive. No change in sign, no extreme value for that candidate. Ready? Let's plug in a value before C1. How about A? What's the derivative at A? Positive. How about at B? Negative. Oops, oh, I did that. Negative slope. So it changed from positive slope to negative slope. Pretend you can't see the graph. If you plug a number into the derivative and you get positive, you plug a number into the derivative and get a negative, could you tell what's happening at that critical number? It's a what? Ready? Here's the number we're looking at. Before it, the slopes were positive. After, the slopes were negative. The function was going up. Came down. That makes it a max. Here, it went up. Horizontal tangent. Up. Kept going up. Not a max. Do you see how to pass the test? The derivative has to change sign. Positive to negative, max. Negative to positive, min. Do you see it? Will that be the case at a sharp point? What if it went like this? Negative derivative, positive derivative. Yes, same thing, right? Ooh, this is going to be a nice test for us. Real nice. Real nice. Let's even call it something. Let's call it the first derivative test. Oops, I didn't mean to erase that. Let's talk more. What do you notice about this problem? It's got some endpoints. Restricted. Doesn't go on forever. It's restricted. I don't know where we're cutting this thing off. I mean, who knows? Maybe we're cutting it off like there, right? It could be. But we know from the extreme value theorem, if f is continuous on a closed interval, it's going to have both a maximum and minimum value. Do you agree? And those endpoints are going to be either max, min, local, or absolute. They're going to be. Because what happens if you start at a point? You start at a point and then start going down. Max. What if you start at an endpoint and you go up? Min. You see it? It's got a lot of stuff going on here. A lot of moving parts. It's almost like it'd almost be good if we had a good a process to follow every single time, wouldn't it? Let's do that. Step 1. Find the derivative, f prime of x. F prime of x equals 6x squared minus 6. Step 2. set f prime of x equal to 0 to get critical points. Critical points. And I'm going to put in parentheses smooth critical points. I'm writing this down, guys? Someone's don't even have a notebook opened up.
I don't honestly.
You're almost
I'm not
too-
hitting the info one right now.
You're almost too comfortable with that.
I'm in
Two
comfy
layers.
mode.
Like-
like
Probably too warm. Starting to fall asleep. Like a baby. Get them all swaddled. Like a swaddled baby.
I'm right now.
All right. Set f prime of x equal to 0 to get smooth critical points. Do you understand what I'm saying there? Well, 6x squared minus 6 equals 0. X squared equals 1. X equals plus or minus 1 are our critical points. Our critical points. -1 and 1. Are you with me? Now I'm going to put a step in here for future use. Step 3, consider if f prime of x does not exist. And I'm going to put sharp critical points. Or maybe f prime of x didn't exist because f didn't exist. Well, I'm not going to put that because why would you try to find a max or a min on f if it didn't even exist there? Right? It had to be continuous first to even have a max or a min at that point. Agree? So I'm just going to put sharp critical points. Does this function have any sharp critical points? Well, f prime is 6x squared minus 6. That exists all real numbers. It's never going to fail to exist. Agree? It's never going to be sharp. None. Step 4. Does the function have any endpoints? And I'm going to put given or implied. I don't know if I like that word. Given or... I'm going to say nat. I like the word natural. They're better. Natural. What are natural endpoints? Well, what about... This is not this problem, by the way. Y equals the square root of x. Doesn't that function have a domain of x greater than or equal to 0? It has a natural endpoint at 0 because you can't plug negatives inside the square root. That would be one where you're not given that it's a domain, but you have to understand it has a natural domain of 0 to infinity. By the way, would that be a minimum value? Square root of x function. Would it have a minimum value at 0? Who votes yes? I vote yes. Well, does this function have any given endpoints? Yeah, -2 and 3. X equals -2. Endpoint. X equals 3. Endpoint. Have we collected every possible situation where this graph could reach a high point or a low point? Where can they come from? Where can they go? No, we're not going there again. They could come from endpoints, interior points that are smooth changes in direction, or interior points that are sharp change. Haven't we considered all of them? So this is by the way, this is not a book process, by the way. That's why I'm writing it down. This is a 5-step process. It's to protect you and make sure you consider every possible situation in the problem. Okay? Step 5. Test for extrema. and this is called, whether it's me or the book or anywhere, it's called the first derivative test. The first derivative test. Well, it's called the first derivative test because we're testing the first derivative. Positive, negative. So on step 5, I'm going to write the first derivative. The first derivative is 6x squared minus 6. F prime of x is 6x squared minus 6. Or 6 times x squared minus 1. Whatever is a more convenient form for you. So if there's endpoints, I put them, this is the x-axis, by the way. This is the x-axis. And again, we're starting with a baby problem so that we see the process so that we can apply it to a more complex problem. You're looking at the x-axis. I need you guys to really focus, okay? If you're thinking about what you're having for lunch today, me too, but hold it for later. All right, pretend you're looking at the x-axis. If we find out what the derivative is doing, even if we don't know the curvature of it, we can tell if the function's going up like this or up like this. I'm sorry, we can at least tell it's going up, right? We're not sure whether it's going up like this or up like this. We won't know until 4-3, all right? But for now, if we plug a number into the derivative, we get a positive. Isn't the function going up? If your velocity is positive, you're going up, right? If you plug it into the derivative, you get a negative. It's going down. That candidate would become a max or a min because of that. So we're looking at the number line, and we're breaking it up into intervals and saying, is the derivative going up or down? What's it doing here? Okay. So what you're going to do is you're going to put x equals -2 here because it's an endpoint. You're going to put x equals 3 over here because it's an endpoint. The other numbers we need to consider are our critical points. Our critical points were -1 and 1. So x equals -1 was a critical point. X equals 1 is a critical point. So can you guys kind of see the y-axis going through here? We're trying to decide, is it going up and down, right? See what I'm doing there? Now, to find out at this critical point, this was a smooth critical point, by the way. So to find out what's happening up until then, we're going to plug a number on this interval into the first derivative. What would be a good test point on this interval? Cool?
-1.5.
-1.5, sure. X equals -1.5 is a test point. I'm warning you right now, if you don't label CP or TP, then you're going to accidentally plug in critical points where you should be plugging in test points. All right, just label them. Where would we plug -1.5 into? The first derivative. It's called the first derivative test. We're testing the first derivative. So here we go. I'm going to write, so I have this x-axis. I'm also going to make almost like a table here, like a table with rows. I'm going to leave this row blank for now, and we're going to be plugging in to f prime. So I'm going to kind of leave this like a row, and we're going to spit out information as we get it. Are you with me so far? Is this confusing? Okay, good. All right. Plug in -1.5 into the first derivative. Ready? And I don't care what the number is. All I care about is positive or negative. -1.5 squared. Well, -1.5 is like -3/2. When you square it, it's 9/4. It's over 2. Do you agree? It's over 2. -1. Positive times 6. Positive. Do you agree? I don't care what the number is. Do you agree? When I plug in -1.5 into the derivative, I get a positive first derivative. Positive. Just at that point, No. Positive first derivative where? Make me proud. Where is the derivative positive? Could I have plugged in negative 1.7? Could I have plugged in negative 1.9? Because the derivative is going to be positive on the whole interval here. But Mr. Westphal, how do I know it's not going to change? How do I know that derivative is not going to change on that interval? You would have gotten another critical point, right? It's not going to change except at a critical point. Okay, so I'm going to actually do this. I'm going to put a interval. F prime is positive on that whole interval. Let's go to the next interval. My test points are going to be purple for this problem. So x equals, what's a good test point between negative 1 and 1? 0. X equals 0. It's a test point. In the first derivative, 0 squared minus 1. Negative 1 times 6. Negative. Negative first derivative between negative 1 and 1. Next interval, maybe 2, x equals 2. Test point. 2 squared, 4, minus 1, 3 times 6, positive. Positive first derivative from 1 to 3. And the only reason I stopped at 3 is because they gave you that as an endpoint. Technically, isn't the derivative positive forever after 1? We just stopped it at 3 because of the problem. Forever. Okay, on this interval, my derivative is positive, meaning my function is going. Let me say it again. On this interval, my derivative is positive, meaning my function is going up. Then it gets to a critical point. What kind of critical point? A smooth one. Then it starts going down. And then it goes to a smooth critical point, and then it starts going up. So I can say confidently on this interval, f of x is increasing, then decreasing, then increasing. You might have found it odd that I did this row, like I wrote it second, but I did it first. Like I wrote it. The reason why, by the time we get to section 4.3, we're going to have a third row called F double prime. And I promised you all year we'd go position, velocity, acceleration in that order. So to stay consistent, I think you'll get this. I'm not trying to reach on this, okay? But if you have a plus or a minus here, then the level above it tells you either increasing or decreasing. For example, if your velocity is positive, your position is increasing. If your velocity is positive, you're moving to the right. If your velocity is negative, you're moving to the left or moving down. Depends on whatever you're talking about. What about acceleration? If your acceleration is positive, then your velocity is increasing. If your acceleration is negative, your velocity is. Do you see how it works? So that's why I organize them in rows like that. Because if you were to switch them, I think it gets a little confusing if you put f of x under f prime. Okay. Well, we're ready. Endpoint right here. I have an endpoint. I don't know how high or how low it is. I don't care yet. I have an endpoint. After the endpoint, do I increase or do I decrease? I increase. If you increase out of an endpoint, that makes the endpoint a minimum. Watch again. I have an endpoint. I increase out of the endpoint. Minimum. It's lower. It's lower than the others. I don't know if it's local or absolute yet. I'm not ready for that. Then I increase and then I decrease. So this point is a minimum. This point is a maximum. This point is a minimum. Now over here, my last endpoint. Am I going up into it or am I going down into it? I'm going up into it. That makes it a max. Now, again, we have the benefit of knowing what this graph looks like. This is a cubic graph. I'm about to mess this all up. It's something like that. Again, it could be translated up or down. I don't know. But that's its behavior. Do you agree? Am I increasing up until here? Yeah. Am I increasing up until here? Yes. Am I decreasing? Yes. Yeah, that's what it looks like. But we're not going to have that benefit all the time. That's okay. Step 6, label. Label extrema. Okay, well, my points were -2, comma, something. And it was blank min. I'm about to label it absolute or local. We don't know yet. It depends on the y value. Next one, -1, comma, -1, comma, blank. Blank max. I don't know yet. Next one, 1, comma, something. Blank min. Endpoint, 3, comma, something. Blank max. The only way you're going to be able to say, oh, that's a min, oh, you're lower, is to know the y values, right? So we should plug these into the, don't say derivative, plug them into the original. F of -2. Well, f of x was 2x cubed minus 6x plus 1. 2x cubed. (2x cubed minus 6x plus 1). -2 cubed is -8 times 2 is -16. -16 plus 12 is -4 plus 1 is -3, I think. Yes? Double checking. I was kind of. Thank you.
It's cubed.
Now, I'm going to go down to the other min because I want to see who wins. Who's the lowest? Well, plug in 1. 1 cubed is 1 times 2 is 2. 2 minus 6 is -4 plus 1 is. Ah, man, that's a tie. Huh. They're both the lowest on the graph. They're both the absolute minimums. It's a tie. Aren't they both the lowest points on the graph? Absolute. Min. Absolute. Min. All right, f of -1. -1 cubed is -1 times 2 is -2. -2 plus 6 is 4 plus 1 is 5. Did you get 5 there?
Yeah.
And f of 3. 3 cubed is 27 times 2 is 54. 54 minus 18. 36 plus 1 is 37. Yeah. Ooh, clear winner. Clear winner. Do. Absolute max. You're just a local. Hello.
Hello.
How are you?
Pretty good.
Thank you. then just for fun, let's graph it on the closed domain. And that's what it looks like. One, -3, -2, -3, -1, comma 4. Nope, 5. -1, 5, and then 327. It's all about where those endpoints cut off the graph as to determine like who's local, who's absolute, right? Does that make sense? How's the process? It's a thorough process. It's 6 steps, kind of tedious. All right, now I want to do a little bit more challenging one to make sure we're understanding how to attack these. And I want to make sure we get to 1 square root function as well. Now, this one just asked for absolute. Do you want to try this one? You guys want to try it? I've been talking a lot. Why don't you guys try it? Follow the steps. I'll kind of follow behind you. I'll write out the step numbers from here on out, but not actually the words of what you're doing in this step. Are we caught up? Or are you just writing down what I'm writing down? Caught up? Any questions so far? Did you find out it didn't have any smooth critical points? The only time a fraction, the derivative is a fraction. The only time a fraction can equal 0 is when its numerator equals 0. Can 2 equal 0? I don't think so. All right, with the thought bubble. How about sharp critical points? Yeah, x equals 0. Oh, wait, x to the 2/3. It's a bit cuspish, isn't it? A little cuspish. Endpoints? Just step 4 is there just to help you consider them. Just remind yourself that they need to be considered. Line them up. Test. Questions on the test? Awesome. Now, labeling. Without a calculator, you're going to have to just kind of decide. All right? I know f of negative 1 is 3, f of 0 is 0. 3 times 2 to the 2/3. I don't know that I put that on a quiz or test without a calculator, but isn't 2 to the 2/3 2 to the 1/3 squared? The cube root of 2 squared? Yes? Times 3. And what are we comparing this to? We're comparing maxes together, aren't we? Max with max. Which one wins? Well, 3 times this number is going to be more than 3, right? It gets the title of absolute max. This one's just a local max. This one, absolute min. So the graph looks something like this. You see it? No smooth changes in direction, just a sharp change in the direction. That one got a min. The other two are endpoints. Make sense? Awesome. All right. One thing I will warn you about. When you do problems like this, you need to write the domain first. Write the domain first. It's going to help you. What is the domain of this? Well, this square root, yesterday's square root to start class was in the denominator. This one's in the numerator. X squared minus 1 has to be greater than or equal to 0 or just greater than 0? The inside of a square root needs to be the inside could be 0. The square root of 0 is 0, right? When is that parabola greater than or equal to 0? Do you remember what I did yesterday? I reminded you of Algebra 2, how you did the number line test and you put plus. Do you really want to do 2 tests? Do you want to do the number line test just to find the domain and then do a number line test for step 5 and the first root? No. You know what I do? Just to think of this one part of the problem, I graph this. Isn't x squared minus 1 that? Where are its zeros? Negative 1 and 1. Question. When is it greater than or equal to 0? Between negative 1 and 1 or beyond negative 1 and 1? Beyond. Guess what you just did? You just wrote your domain. Your answer to that question is the domain of this function. The answer to that question is the domain of this function. Negative infinity to negative 1. Inclusive, bracket, union, 1 to infinity. Whatever infinity you prefer. All right. Question. What's the derivative? I don't want to go through all the whole problem, but I want to help you. Okay? dy dx. 1/2. Leave the inside alone. Subtract 1 from the exponent times 2x. Okay. The derivative of this thing. X over the square root of x squared minus 1. That's the derivative. Step 1. Step 2. What's step 2? Set equal to 0. A fraction equals 0 when it's... So x equals 0 is a critical point. Smooth or sharp? Smooth, but wait a minute. The domain of this function didn't include 0, did it? It's out. See ya. All right. Step 3. When does the derivative fail to exist? Isn't it when this thing is 0 or less than 0? Isn't that the complement of its domain? It's an interval. I don't want to do that. I can't have a max or a min on that interval. The function doesn't exist there. But it does at the natural endpoints of this function. What are the natural endpoints of this function? -1 and 1. It goes -1. Now, that's not, I'm not graphing, by the way. This is not the graph of the original. This was the graph to get you the domain. The original function could go like this. I don't know how, but it's here and here. So -1 could be a max or min, couldn't it? +1 could be a max or min. Do you see where I'm going with this? These are tough. These can be tough because of the algebra of it. The algebra on these could be tough. So be careful. That's just to get you thinking. All right. I think I have the homework assignment written out. Let me double check it. I wasn't quite sure how far we're going to get today, so don't write this down yet. Oh, that was weird. I think I copied some from yesterday because I wasn't going to give you guys much. How did 1 through 4 go last night? Easy. All right, we're not doing 5, 6, and 8. Those are just similar ones. If you thought last night's was easy, you don't need to do those. All right. $19, $21, $23. Oh, you want to complain? You want to start complaining? That's all I was going to give you, but if you guys want to complain, I'll give you more. What, are we in agreement now? I don't care. It's not a democracy. 4 problems. Have fun. Yeah, and they started complaining at it. I know you wouldn't complain.
I would never complain. I'm just blessing this opportunity.